The Mariana Trench is the name everyone knows, the deepest place on Earth, the abyss at the bottom of the world that has captured the human imagination for decades. But depth is not the same as violence, and in the South Pacific, there is a trench that the Mariana cannot match, not in the speed at which it is consuming the ocean floor, not in the earthquakes it generates from depths where rock should barely be able to fracture, and not in what it has already shown the world it is capable of. The Tonga Trench is swallowing the Pacific Plate at a rate roughly 6 times faster than the Mariana. The ground beneath the South Pacific is disappearing into the Earth faster than almost anywhere else on the planet, and the surface gives no sign of it. Thousands of kilometers of open ocean stretch above it, calm and featureless, while underneath, one of the most geologically active places on Earth tears itself apart in slow motion. In January 2022, something above the trench reminded the world that this part of the ocean is not quiet. A volcano erupted with a force that registered as the largest eruption ever recorded by modern scientific instruments. The shockwave it produced traveled around the entire planet. It was heard thousands of kilometers away. The plume it sent into the atmosphere climbed higher than almost anything in recorded history. And beneath all of that, beneath the eruption and the earthquakes and the vanishing ocean floor, when humans finally reached the bottom of the Tonga Trench, they found something nobody expected. A seafloor unlike the bottom of almost any other major trench on Earth, untouched, unmarked, as if the violence above had kept the world away long enough for the darkness below to remain completely its own. Almost nobody talks about the Tonga Trench. Almost nobody knows what is happening beneath it. Tonight, we go down. Before we descend, if stories like this are what keep you curious, give the video a like and subscribe. It helps us keep exploring places most people will never see. Let's descend into one of the most violent places on Earth. The Tonga Trench begins with a meeting between two enormous pieces of Earth's crust, a meeting that has continued for roughly 50 million years. Far below the South Pacific, the planet's outer shell is divided into great moving plates. They drift across the softer material beneath them, carrying oceans and continents as they go. Their movement is measured in inches each year, yet across geological time, those inches reshape entire worlds. Earth has roughly 15 major tectonic plates, each following its own path. The Pacific Plate is the largest oceanic plate, covering more than 40 million square miles of seafloor and moving generally westward. To its western side, the Indo-Australian Plate meets it across the complex boundaries of the South Pacific. Farther away, that same plate helps build the Himalayas and contributes to the tectonic forces shaping New Zealand. Here, its meeting with the Pacific Plate creates a very different landscape. When two oceanic plates converge, their histories matter. Older oceanic crust has had more time to cool, making it denser than younger crust. The denser plate can descend beneath the other. This process is called subduction, meaning one tectonic plate dives beneath another and sinks into the mantle. The movement is gradual, measured over immense spans of time, yet it produces some of the deepest structures on Earth. As the Pacific Plate bends downward, the seafloor follows that curve. Rock that once formed part of a broad ocean floor is carried toward the planet's interior, creating a long depression along the boundary. That depression is the Tonga Trench. It stretches for about 850 miles across the South Pacific, running alongside the islands of Tonga like a long crease in the ocean floor. The crust itself is thin compared with the planet beneath it, yet it is strong enough to carry oceans across the globe. At a boundary like Tonga, that strength allows the Pacific Plate to remain intact while its leading edge folds downward. The descending section becomes part of a much larger journey through the mantle, carrying the history of the seafloor with it as it goes. At its deepest point, the horizon deep reaches 10,823 meters, which is about 35,509 feet below sea level. That is nearly 6.7 miles of water pressing downward toward the seafloor. The depth makes it the deepest known point in the southern hemisphere, giving the trench a place among the most extreme environments on the planet. The shape of this boundary is only the beginning. One plate approaches, bends, and descends. The other remains above it, forming the foundation for the volcanic island arc and the ocean basin beyond. Every earthquake, every eruption, and every change in the surrounding seafloor grows from this basic arrangement of moving rock. Seen from the surface, the South Pacific offers little indication of the structure beneath it. The ocean stretches across thousands of miles, while the boundary below continues its patient motion. The Tonga Trench is therefore less like a scar fixed into the seabed and more like a moving seam, where one part of Earth is continuously carried downward and another remains above. With that structure in place, the unusual character of Tonga becomes easier to recognize. The plates are not merely meeting here, they are moving toward one another at a pace that makes this boundary exceptional. A number emerges from the instruments before the landscape around Tonga seems to change at all. At stations across the northern part of the trench, measurements show the Pacific plate converging at a rate of up to 9.4 inches each year. That is more than 6 times the movement measured along the Mariana Trench, placing Tonga at the highest measured plate convergence rate on Earth. 9.4 inches can feel almost ordinary when spoken aloud. Spread across a year, it is less than the width of a hand. Across a century, however, the same motion becomes more than 78 feet, which is about 24 meters. The important part is its persistence. The boundary does not make that journey in a single dramatic movement. It advances through thousands upon thousands of small adjustments, each one adding to the same long descent. For comparison, the San Andreas Fault moves at roughly 1.5 inches per year. Tonga therefore advances more than 6 times faster. The Mariana Trench converges at approximately 1.6 inches per year, making its motion around 6 times slower. The difference is striking because both boundaries consume oceanic crust, yet their engines operate at very different speeds. Several forces meet within the Tonga system. The Pacific plate continues toward the boundary, while the opposing plate resists its arrival. At the same time, the Lau Basin behind the volcanic arc is spreading outward. New crust forms along its spreading centers, allowing the arc to retreat relative to the trench. That retreat helps draw the subducting Pacific plate toward the mantle, adding another component to the motion. The geometry of the descent matters as well. The Pacific slab enters the Earth at an angle of roughly 55 degrees. Picture a broad sheet of cold oceanic rock turning downward along a steep curve. Gravity acts on the dense slab, while the surrounding plates and spreading basin influence its movement. Together, these forces create a system whose northern section moves especially rapidly. The speed also varies along the trench. The northern Tonga region carries the highest measured convergence rates, while sections farther south move more gradually. This uneven motion gives scientists a natural way to compare different parts of the same plate boundary. Global positioning system instruments on islands and other fixed points record tiny changes in position, allowing researchers to watch the boundary advance without ever seeing the rock itself move. Those measurements reveal something important about the nature of this process. There is no need for a single giant event to account for the yearly displacement. The plate is being carried downward continuously, Year after year, the ocean floor approaches the trench, bends, and begins its descent. The number on a positioning record is therefore a measurement of disappearance, translated into distance. The remarkable speed has another consequence. Oceanic rock entering the mantle carries the temperature it acquired during its long journey across the seafloor. A rapidly descending slab has less time to exchange heat with its surroundings before reaching greater depths. Its interior can therefore remain colder and more rigid as it travels downward, preserving a property that becomes increasingly important under enormous pressure. Cold rock behaves differently from warm rock when the planet begins to squeeze it, and the difference reaches far into the descending slab. Temperature is usually the first thing that changes as oceanic rock begins its descent. The seafloor has spent millions of years cooling, yet once a slab enters the mantle, the warmer material surrounds it on every side. Heat gradually moves inward. The rock loses some of its rigidity and begins to deform, bending and flowing under pressure instead of breaking into sudden fractures. That transition places a natural limit on how deep ordinary earthquakes can occur. Across many subduction zones, seismic activity becomes scarce below roughly 180 miles and often fades by about 250 miles. At those depths, heat has had enough time to transform much of the descending plate. Rock that can flow may still carry enormous stress, but it cannot release that stress through the brittle fractures that generate conventional earthquakes. Tonga follows a different thermal path. The Pacific slab is moving downward so rapidly that heat cannot penetrate its interior as efficiently as it does in slower systems. The outside of the slab interacts with the surrounding mantle, while its core retains the colder character of oceanic lithosphere. Rigidity therefore survives far deeper than expected, allowing the descending rock to carry stress into regions where ordinary slabs have already become too warm to fracture. The difference reaches extraordinary depths. Earthquakes associated with the Tonga slab have been detected as far as about 430 miles below the surface. That depth approaches the deepest boundary at which seismic activity is known to occur anywhere within the mantle. Here, pressure reaches roughly 200,000 times the pressure at sea level. Temperatures rise above 2,000 degrees Fahrenheit. Even in those conditions, portions of the slab can still undergo sudden failure. The physics becomes especially interesting around the mantle transition zone. At approximately 410 miles below the surface, minerals encounter pressures high enough to rearrange their crystal structures. The material remains chemically similar, yet its atoms occupy different arrangements that are stable under the greater compression. This transition changes how seismic waves travel through the mantle and alters the mechanical behavior of the descending plate. A cold slab approaching this boundary carries a thermal history unlike that of warmer material. Its lower temperature affects how minerals transform, how water may be stored within their structures, and how the slab couples mechanically with the surrounding mantle. Seismic waves generated inside the plate become natural probes of these processes. Each event provides a trace of how a piece of oceanic crust behaves while crossing one of the most inaccessible regions of the planet. There is also a strange relationship between speed and survival. The faster the slab travels, the less opportunity the surrounding mantle has to erase its thermal contrast. The colder interior preserves strength, and that strength allows stress to accumulate farther down. Pressure alone does not guarantee that rock will fracture. Temperature determines how that pressure is expressed, whether the material bends over time or releases stored energy through a sudden rupture. The Tonga slab therefore carries a record of its descent within its own physical structure. Its temperature, rigidity, mineral transformations, and fractures are connected parts of one process. far below the ocean. Rock that should have softened remains capable of breaking, allowing earthquakes to originate at depths where the ordinary rules of shallow crustal behavior no longer apply. Deep earthquakes occupy a special part of Earth's interior, far below the region where most familiar shaking begins. Scientists classify them by depth. Shallow earthquakes occur above about 43 miles. Intermediate earthquakes extend from roughly 43 to 186 miles. Deep focus earthquakes begin below 186 miles, entering a realm where pressure and temperature change the behavior of rock itself. Tonga stands apart within this deepest category. More than 65% of the world's deepest earthquakes occur within its subduction system, with many originating 300 miles or more below the surface. These events are valuable because they reveal that the descending Pacific slab remains mechanically active long after it has entered the mantle. The earthquake sources form a trail through the interior, following the plate as it sinks. The strange part is what an earthquake requires. Near the surface, rock can fracture when stress overcomes its strength. Farther down, pressure presses microscopic cracks closed, while heat encourages minerals to deform and flow. Under those conditions, conventional brittle failure becomes increasingly difficult. Something else must allow stored energy to escape. One leading explanation involves transformational faulting. Minerals inside the descending slab can undergo rapid changes in crystal structure as pressure increases. The atoms rearrange into denser forms, and that transformation can weaken a narrow region within the rock. If the change spreads rapidly enough, it can release stored energy as seismic waves. The process resembles a fracture in its effects, even though the underlying mechanism is governed by mineral transformation rather than an ordinary crack opening through cold rock. The Tonga record gives scientists an unusually rich collection of these deep events. Between 1976 and 2022, researchers identified 430 earthquakes larger than magnitude 4.7 at depths below 400 miles in the southern Tonga region alone. Such a concentration makes the slab resemble a natural instrument, producing repeated signals from depths that no human drill could approach. On August 19, 2002, two deep earthquakes of magnitude 7.6 and 7.7 occurred on the same day within the Tonga system. Their close sequence provided evidence for dynamic triggering, in which seismic waves from one earthquake change stresses far enough away to help initiate another event. The connection between individual ruptures can therefore extend through the slab itself. Other earthquakes have reached even greater scale. A magnitude 8 earthquake struck near the Tonga Trench on May 3, 2006. 3 years later, on September 29, 2009, a magnitude 8.1 event occurred along the outer trench slope. An earthquake of magnitude 8 releases energy comparable to roughly 6 million tons of TNT, enough to make a single rupture significant across an enormous region. The earthquakes are distributed through the slab's interior, tracing different stresses and mineral changes as it travels downward. Their depth reveals its persistence. Their frequency reveals its activity. Their individual sequences reveal a structure within the rock itself, where separate layers can respond differently to the same descent. The Tonga slab, therefore, behaves less like a single rigid object than a complex body carrying several kinds of stress at once. Its earthquakes mark those internal divisions, creating a pattern that can be read through seismic waves long after each rupture has passed. A seismic map of the Tonga slab reveals an unusual pattern. Earthquakes do not form one continuous ribbon through the descending rock. They arrange themselves into two nearly parallel bands, creating what geologists call a double seismic zone. One band follows the upper part of the slab, while another lies deeper within it, with a corridor of comparatively little seismic activity separating them. The two bands reflect different kinds of stress. As the slab bends downward toward the mantle, its outer surface is stretched. The upper portion is pulled across the curve, placing the rock under tension. Where that tension exceeds the strength of the material, fractures develop and seismic energy is released. The earthquakes along this upper band therefore mark the mechanical strain produced as the plate changes direction. Farther inside the slab, the pattern changes. Compression becomes more important as the descending plate is pressed against the surrounding mantle. Rock in this region is squeezed from several directions while continuing its downward journey. That compression can also generate earthquakes, producing the second band beneath the first. Two different stresses are therefore written into the same piece of oceanic crust. Between them lies a zone where seismic activity becomes much less common. The separation is roughly 12 to 18 miles wide. This interval occupies the transition between the tension affecting the upper surface and the compression acting deeper inside. The stresses do not vanish, yet the conditions favor fewer detectable ruptures. The result is a narrow layer of relative seismic calm enclosed by two active bands. Tonga's double seismic zone is unusually persistent. The paired bands can be distinguished down to about 186 miles, considerably deeper than comparable structures documented at other subduction zones. Their persistence gives researchers a rare opportunity to follow how stress changes inside a slab as it travels through the mantle. The pattern also carries information about the slab's physical condition. The spacing between the earthquake bands can help estimate the thickness of the seismically active portion of the plate. Their distribution provides clues about temperature, strength, and the direction of forces acting through the descending rock. Seismologists can reconstruct this internal architecture from the timing and location of thousands of seismic waves, much as a distant scan can reveal the shape of something that cannot be opened or reached directly. That makes the double zone more than an unusual arrangement on a map. It is a natural record of mechanical conditions deep inside Earth. Every earthquake contributes another point to that record, allowing researchers to compare different depths and trace changes as the slab descends. Most subduction zones do not display such a clear, persistent pair of seismic bands. Some show hints of the pattern, while others produce a more diffuse distribution of earthquakes. Tonga offers a particularly well-defined example, extending through a substantial portion of the descending plate. The structure also reveals that a subducting slab is not responding to pressure as one uniform body. Different parts can experience different forces at the same moment, separated by only a relatively narrow distance. The upper surface stretches, the interior compresses, and the space between them records the boundary between those opposing mechanical regimes. Together, the two bands form a deep seismic signature of the plate as it bends, descends, and continues into the mantle. A volcano can begin far below the place where its lava eventually appears. Along the Tonga Arc, the first ingredients arrive from the descending Pacific slab. As that slab sinks, minerals within the oceanic crust release water and other volatile compounds under increasing pressure and temperature. Those materials rise into the mantle above, entering a wedge of rock that would otherwise remain largely solid. Water changes the balance. It lowers the melting temperature of mantle minerals, allowing portions of the surrounding rock to melt under conditions where they might normally remain solid. The newly formed magma is less dense than the rock around it, so it begins to rise. Some gathers in reservoirs within the crust. Some continues upward, following fractures and pathways created by the moving tectonic system. This process produces the Tonga volcanic arc, a chain of more than 30 active or recently active volcanoes extending for roughly 500 miles alongside the trench. Much of this volcanic landscape exists below sea level. Submarine volcanoes grow upward from the ocean floor, building seamounts whose summits may remain underwater for their entire lives. Their eruptions can release heat, gases, ash, and fragments into the surrounding ocean without ever producing an island. In deeper water, immense pressure also changes how expanding volcanic gases behave, allowing some eruptions to remain confined beneath the surface. The ocean absorbs much of their heat, while the seafloor records each episode through fresh layers of volcanic material. Where volcanic peaks do reach the surface, they become islands. Tonga is therefore part of the same geological arrangement that begins with the descending slab. The land supporting communities and forests is the uppermost expression of a process reaching from the ocean floor into the mantle. The boundary below and the volcanic chain above are connected through the movement of water, minerals, heat, and magma. The character of that system is influenced by the speed of subduction. A faster descending plate can transport volatile rich material into the mantle more efficiently, supplying the melting region above with a steady stream of ingredients. Greater volatile delivery can encourage greater magma production, although the relationship depends on the chemistry of the slab, the mantle, and the pathways through the crust. Volcanic intensity, therefore, emerges from several linked processes rather than one simple measure. The arc also changes with distance and depth. Individual volcanoes have different magma sources, different histories, and different eruption styles. Some build broad underwater mountains. Others form steep volcanic islands. Their differences reflect variations in crustal thickness, magma storage, fluid release, and the structure of the mantle beneath them. Seen together, these volcanoes form a chain that records the journey of the Pacific slab. Every eruption represents material that began much farther away, traveled downward into Earth, released its water and other volatile compounds, and helped generate molten rock above. The journey crosses enormous changes in pressure, temperature, and physical state. The connection reaches its most concentrated expression when an underwater volcano grows large enough for seawater, magma, gas, and collapsing rock to interact within a confined space. At such a volcano, the boundary between the ocean and the interior of Earth becomes a place of rapid transformation, with consequences that can spread far beyond the volcano itself. On the morning of January 15th, 2022, the ocean around Hunga Tonga, Hunga Ha'apai changed in a matter of minutes. The submarine volcano rose from the seafloor north of Tonga, and at 4:14 Coordinated Universal Time, its eruption entered a phase so energetic that the atmosphere itself became part of the event. The explosion was extraordinarily concentrated. Water surrounding the volcano was driven aside as expanding gas, steam, ash, and fragmented rock surged upward. The eruption produced an explosive energy estimate ranging from roughly 4 to 18 megatons of TNT, while other studies have produced larger estimates for the total energy of the broader event. The important measure was not a single number, but the extraordinary pressure pulse that followed. That pulse became a Lamb wave, a broad atmospheric pressure disturbance capable of traveling along the surface of the planet. Instruments around the world recorded it as the disturbance passed. The wave traveled around Earth multiple times, with researchers detecting 4 complete passages and additional waves moving along different paths. For a natural event, the global reach was extraordinary. Its atmospheric signature also placed Hunga Tonga in a category of its own within the modern instrumental record. Measurements of the pressure wave were comparable to those produced by the largest historical atmospheric nuclear test, while the volcanic event itself had a much longer pressure wave period. The closest historical comparison in atmospheric wave behavior was the 1883 eruption of Krakatoa, whose effects were recorded across enormous distances. Above the volcano, the eruption column rose through the atmosphere at a speed that made its height difficult to comprehend. Satellite observations placed the highest part of the plume at about 58 kilometers, which is about 36 miles. It reached the mesosphere, carrying ash, volcanic gases, and an extraordinary quantity of water vapor into regions that volcanic eruptions rarely reach. The plume climbed to that altitude within roughly half an hour, forming a towering column above the Pacific. The water vapor was especially unusual. Scientists estimated that the eruption injected more than 140 billion kilograms of water into the stratosphere, an amount large enough to alter atmospheric chemistry and circulation for years. Unlike ash, which gradually settles, water vapor can remain aloft and spread through the atmosphere, giving the eruption effects that extended far beyond the immediate region. The ocean responded as well. The eruption generated tsunami waves through several interacting mechanisms, including the collapse of the water cavity created by the underwater explosion and the coupling between atmospheric pressure waves and the sea surface. The pressure disturbance traveled much faster than an ordinary earthquake-generated tsunami, allowing water level changes to appear across distant coastlines. In Peru, more than 10,000 kilometers away, which is about 6,200 miles, the resulting coastal disturbance contributed to 2 deaths. Tide gauges around the Pacific recorded unusual sea level changes, showing that an eruption beneath a remote island could influence an ocean basin on the other side of the planet. Across the Pacific, the eruption was also heard as distant atmospheric sound, while pressure sensors registered the passage of the disturbance. A single underwater volcano had reached across ocean and atmosphere together. Hunga Tonga therefore became more than a volcanic eruption. For several hours, the ocean, atmosphere, and solid earth behaved as one connected system, carrying the disturbance outward through every layer it touched. A warning siren depends on a particular sequence. An earthquake shifts the sea floor. The ocean above it rises or falls. Instruments detect the shaking, and computers estimate how quickly the resulting waves should reach the coast. For most tsunamis, this chain creates a precious interval between the first disturbance and the arrival of water. Hunga Tonga introduced a different kind of clock. On January 15th, 2022, the eruption generated an enormous atmospheric pressure wave that raced outward from the volcano. Known as a lamb wave, this broad disturbance moved through the lower atmosphere while pressing against the ocean surface. Its speed reached roughly 1,159 kilometers per hour, which is about 720 miles per hour. The ocean responded to that moving pressure field, producing changes in sea level that traveled with the atmosphere rather than beginning as a conventional earthquake, tsunami. The process has a name, Proudman resonance, when an atmospheric pressure disturbance moves across the ocean at a speed close to that of shallow water waves. The two motions can reinforce one another. Each passing pulse gives the water another small push, allowing the ocean response to become much larger than the pressure disturbance alone might suggest. Around the Pacific, tide gauges began recording unusual movements as this atmospheric wave crossed the basin. That created a problem for warning systems designed around earthquakes. Seismometers are excellent at identifying the ground motion associated with tectonic events, yet Hunga Tonga's most important early signal was moving through the atmosphere. The eruption did produce seismic activity, but the first ocean disturbances did not follow the familiar sequence of a large earthquake, causing widespread seafloor displacement and then sending a tsunami outward. The atmospheric route allowed water level changes to appear at distant shores on a timescale that conventional models could not fully anticipate. Along the coasts of Chile and Peru, tide gauges recorded unusual sea level changes while agencies were still assessing the eruption and its consequences. In Peru, the coastal disturbance contributed to two deaths. Damage across the Pacific reached into the hundreds of millions of dollars, while ports and shore facilities experienced currents and water level fluctuations that differed from the patterns expected from a standard seismic tsunami. The event exposed a gap in a system built from decades of experience with earthquake generated waves. Atmospheric pressure forcing had been recognized by scientists before, and the possibility of weather and volcanic disturbances influencing ocean levels was known. What had never been demonstrated on this scale was the ability of a major volcanic pressure wave to produce a basin-wide coastal signal with such unusual timing in the first critical moments of an eruption. Afterward, tsunami researchers and warning agencies began examining ways to incorporate atmospheric observations alongside seismic and ocean measurements. Barometers, satellites, tide gauges, and eruption monitoring can provide pieces of the same event from different layers of the Earth system. The lesson was not that earthquake-based warnings had failed universally, but that the ocean can receive energy through more than one pathway. Hunga Tonga had shown that a tsunami warning system must sometimes listen upward as well as downward. The atmosphere can become part of the ocean's motion, and a pressure wave can carry a disturbance across an entire basin before the usual chain of detection has fully formed. On the western side of the Tonga system, the seafloor is being made even as the Pacific plate disappears on the eastern side. The Lau Basin lies between the volcanic arc and Fiji, forming a broad stretch of ocean that reaches roughly 400 kilometers, which is about 250 miles, across near its northern end. Farther south, its shape narrows, following the changing geometry of the arc. Here, the plate above the descending Pacific slab is being pulled apart. This process is called back arc spreading. As the trench retreats toward the east, the volcanic arc is stretched behind it. The crust thins, fractures, and allows molten rock from the mantle to rise into the opening. That molten material cools into basalt, adding fresh oceanic crust to the floor. The seafloor beneath the Lau Basin is therefore part of a geological process that can be watched through measurements made across the ocean. The basin began opening roughly 6 million years ago as the Tonga Trench accelerated its retreat and the surrounding crust responded to the changing forces. Since then, spreading has produced a complicated pattern of ridges and volcanic centers. In the northern Lau Basin, several spreading centers operate close together, giving scientists an unusually clear view of how a back arc develops while subduction continues nearby. At the fastest northern centers, new crust forms at about 16 centimeters per year, which is about 6.3 inches. That may sound small beside the dimensions of an ocean basin, yet each year another layer of basalt is added to the floor. Over thousands and millions of years, these small movements become measurable stretches of newly created seafloor. The process also brings heat and chemical compounds from the mantle into the ocean, supporting unusual ecosystems around hydrothermal vents. The geometry becomes especially interesting when the two sides are considered together. The Pacific plate can converge toward the trench at roughly 24 centimeters per year, which is about 9.4 inches, while the Lau Basin can spread at roughly 16 centimeters per year, which is about 6.3 inches. One boundary consumes oceanic crust, as another produces it nearby. The two motions are linked through the same shifting plate system, with the trench retreating as the basin opens behind the arc. This arrangement gives the region an unusual geological rhythm. Material that once rested beneath the Pacific Ocean can begin its descent into the mantle, while mantle material elsewhere rises, cools, and becomes part of the ocean floor. Destruction and construction occur within the same broad system, separated by only a few hundred miles. The crust is continually rearranged, with one portion moving downward while another portion takes shape. For scientists, the Lau Basin provides a natural setting for observing how subduction can reshape an entire plate boundary. Seismic activity, volcanic eruptions, spreading ridges, and hydrothermal systems all belong to the same connected engine. The Tonga region, therefore, carries two opposing motions within one landscape, consumption on one side and creation on the other. That contrast also gives the trench a deeper perspective. The Pacific seafloor is being removed at extraordinary speed, while fresh crust emerges nearby to occupy the changing space. The ocean here is both ending and beginning, with the boundary between those two processes written into the shape of the seafloor itself. For nearly 6 decades, the Tonga Trench occupied an unusual place in exploration history. It was one of the deepest places on Earth, yet its floor remained beyond human reach, while another trench repeatedly drew explorers, cameras, and research vessels toward its deepest point. On January 23, 1960, Don Walsh of the United States Navy and Jacques Piccard of Switzerland descended inside the bathyscaphe Trieste and reached the Challenger, deep in the Mariana Trench. Their descent became one of the defining moments of ocean exploration. They had entered the deepest known part of the planet and returned with direct knowledge of a place that had previously existed only through measurements and inference. The Mariana continued to attract attention long after that first descent. James Cameron reached the Challenger Deep alone in 2012, spending hours on the seafloor while recording the environment around him. In April 2019, Victor Vescovo returned during the Five Deeps expedition and established another milestone in deep ocean exploration. The Mariana had become a destination that could be revisited, mapped, photographed, and studied from multiple angles. Tonga waited much longer. On June 10, 2019, Vescovo descended aboard the Deep Submergence Vehicle, limiting factor, and reached the horizon deep. The dive formed part of the Five Deeps expedition, an effort to reach the deepest point in each of the world's 5 oceans. After 59 years, a human presence finally reached the floor of the Tonga Trench. The delay was not caused by an absence of suitable engineering. By the time the limiting factor arrived, deep diving technology had already demonstrated that human beings could survive immense pressure and operate specialized vehicles at extraordinary depths. The vehicle itself had been designed for repeated descents into the deepest environments of the global ocean, allowing the expedition to visit several Hadal sites within a single year. A different force had shaped the delay, one that belongs to the language of exploration itself. The Mariana carried the clearest superlative. It held the deepest point on Earth, a distinction that could be expressed in a single sentence and understood immediately. Tonga was slightly shallower, by roughly 150 meters, which is about 490 feet. In the culture of exploration, that small numerical difference created a large difference in attention. During those 59 years, The Tonga system continued its geological work without an audience at the seafloor. Deep earthquakes traveled through its descending slab. Volcanoes rose along the arc. The Lau Basin generated new crust nearby. Life occupied the hadal floor, adapting to pressure and scarce food while remaining almost entirely beyond direct human observation. That absence matters because measurements from instruments above the trench can reveal only part of the world below. A seafloor photograph can show texture, sediment, animals, and debris in ways that distant sensors cannot. A human-operated vehicle can follow subtle changes across the bottom, examine objects from different angles, and connect physical observations with the geology around them. The horizon deep, therefore, remained more than a number on a depth chart. For generations, it was a place known through soundings, calculations, and distant signals. Then, in 2019, the boundary between measurement and experience finally disappeared. Vescovo's descent brought a human observer into a landscape that had endured for millions of years without one. The descent began as a measured disappearance from the world above. On June 10th, 2019, Victor Vescovo guided the limiting factor toward the horizon deep, entering a column of water that would eventually press against every part of the vehicle. For hours, the ocean became the entire landscape, with no horizon, no familiar scale, and no natural reference for distance. The vehicle was built around a titanium pressure hull designed for full ocean depth. As it descended, the pressure increased steadily, while the surrounding water became colder and denser. The journey to the bottom took approximately 4 hours, carrying Vescovo into a realm where even a small mechanical failure could become decisive. At the end of that descent, the instruments recorded a depth of 10,823 meters, which is about 35,509 feet. Direct pressure measurements confirmed the horizon deep as the deepest point in the southern hemisphere and the second deepest known location in any ocean. What appeared below was not a smooth depression waiting at the bottom of a long shaft. The seafloor carried its own shape, with ridges, scarps, sediment, and small basins forming an irregular geological surface. Measurements of temperature and water chemistry added another layer to the picture. Even here, where the weight of the ocean reached its greatest intensity, the floor remained part of an active landscape shaped by the movement of Earth's crust. Then there was the absence of something far more familiar. No obvious human debris was reported from the horizon deep during the expedition. That observation became striking when placed beside discoveries from other trenches. At the Challenger Deep in the Mariana Trench, Vescovo had encountered plastic during dives only weeks earlier. A plastic bag was observed near the deepest part of that trench, while other studies have documented synthetic particles and human debris in its extreme depths. The difference extended beyond the Mariana. Deep environments in other major trenches have also shown traces of human activity carried downward through currents, sinking material, and the gradual movement of particles through the ocean. Industrial civilization had reached places separated from the surface by kilometers of water long before most people had ever imagined visiting them. At horizon deep, the expedition reported no visible signs of human contamination. The finding did not mean that the trench was isolated from every substance carried through the ocean, nor could a single descent establish permanent purity across an entire ecosystem. It meant that the first direct human examination found a seafloor remarkably free of the obvious debris seen elsewhere. Across the floor, sediment settled in patterns shaped by currents and gravity. That distinction gave the descent a second meaning. The expedition had come to measure depth, map terrain, and understand the physical character of a place shaped by one of Earth's most active tectonic systems. Instead, the first human visit also provided a rare glimpse of a deep environment before recognizable traces of modern civilization had become part of its scenery. The horizon deep had spent millions of years being shaped by forces far beyond human reach. When someone finally arrived, the most striking discovery was how little human history had arrived with them. The floor remained a living geological surface, and within it, organisms had already made their own home. At the floor of the horizon deep, the weight of the ocean becomes a physical force unlike anything experienced on land. At a depth of 10,823 meters, which is about 35,509 feet, pressure reaches roughly 110 megapascals, which is about 16,000 pounds per square inch. That is more than 1,000 times the pressure at sea level. A car tire carrying about 240 kilopascals, which is about 35 pounds per square inch, experiences only a tiny fraction of the force surrounding the trench floor. For a human body, such pressure would be immediately fatal. Air spaces would collapse, delicate tissues would fail, and the chemistry that allows cells to function at ordinary surface conditions would be pushed far beyond its normal range. The trench itself, however, is filled with organisms whose bodies have been shaped around those conditions across immense spans of evolutionary time. The water at the bottom remains close to freezing, around 2 degrees Celsius or 36 degrees Fahrenheit. There is no sunlight to warm it, no daily cycle of heating and cooling, and no changing season in the ordinary sense. Food arrives from above in scattered particles, organic fragments, and the remains of organisms carried downward through the water column. Life here has learned to make use of a sparse and irregular supply. Even the chemistry inside a cell must change under pressure. Cell membranes contain greater proportions of unsaturated fatty acids, allowing them to remain flexible when intense pressure would make ordinary membranes too rigid. Proteins face another problem. Extreme pressure can distort their three-dimensional structures, interfering with the precise shapes required for enzymes to function. Some deep-dwelling organisms use compounds called piezolites, small molecules that help stabilize proteins and preserve their working form. These adaptations belong to the Hadal zone, the deepest ecological region of the ocean, beginning at approximately 6,000 meters, which is about 19,700 feet. Far from being an empty boundary beneath the familiar ocean, it contains communities with predators, scavengers, microbes, and organisms that recycle material falling from above. Their relationships form food webs adapted to darkness, cold, scarcity, and pressure. Reaching this environment also demands unusual engineering. The submersible used to visit the horizon deep relied on a titanium pressure hull capable of protecting its occupants from the surrounding force. Its electronic systems were designed around the same problem. Some components were pressure compensated, while others were sealed within oil-filled chambers so the pressure could be balanced across their surfaces. Ordinary equipment designed for the surface cannot be carried downward without careful adaptation. The remarkable part is the correspondence between machine and organism. The submersible survives by controlling pressure around its most vulnerable systems. Hadal organisms survive by changing the chemistry of the systems within their own bodies. Both are responses to the same physical reality, expressed through entirely different histories. At the bottom, pressure is no longer an obstacle that life must endure for a short journey. It is part of the environment that shaped every membrane, protein, reaction, and relationship in the community. At 10,823 meters, which is about 35,509 feet, one group of animals has taken that pressure even further, turning the force itself into part of its survival strategy. The deepest reaches of the horizon deep belong to animals that resemble tiny shrimp, yet their success depends on a place where almost nothing else can follow. Their small bodies move across sediment and debris, searching for organic particles delivered from the world above. Amphipods are common crustaceans across the ocean, often living as scavengers and feeding on material that drifts downward. In the hadal zone, some have become specialists for pressures that would overwhelm most related animals. One of the important species in the Tonga system is Hirondelia dubia, a hadal amphipod recorded across several South Pacific trenches. Its body is adapted to extreme pressure, allowing it to live at depths approaching 10,800 meters, which is about 35,400 feet. At these depths, survival depends on chemistry, metabolism, and physiology working together under conditions that exclude most potential competitors. A revealing experiment came from a 2018 expedition. Researchers placed baited traps at two levels inside the Tonga Trench. One rested at 6,250 meters, which is about 20,500 feet. The other was positioned at 10,800 meters, that is nearly 35,400 feet. The difference between the communities was striking. At the shallower station, several amphipod species gathered around the food. Different forms shared the same resource, creating a community with greater diversity and stronger competition. At the deeper station, the pattern changed. Hirondelia dubia was the only amphipod species recovered, yet the number of individuals was roughly 7 times greater than at the shallower site. That arrangement suggests a remarkable ecological division. Young amphipods, which have not yet developed the full physiological adaptations required for maximum depth, remain higher in the trench. There, they encounter other species and compete for scattered food. Mature Hirondelia dubia can descend farther, entering a zone where the surrounding pressure becomes a barrier against competitors that cannot tolerate it. Scientists describe this pattern as ontogenetic vertical stratification, age and development influence where an animal can live, creating different depth ranges within the same species. For these amphipods, adulthood brings access to an environment with fewer competitors and a concentrated supply of organic material along the trench axis. The pressure that limits other animals, therefore, helps separate the adults from the crowded waters above. Size adds another dimension. Deep-dwelling Hirondelia dubia can become larger than related amphipods found at shallower levels. Reduced competition allows more access to food, while life at extreme depth imposes its own metabolic demands. Their bodies are shaped for a world where pressure is constant and resources arrive irregularly. This makes the deepest trench floor more than a place where these animals happen to survive. Their distribution suggests that depth itself has become part of their ecological strategy. The farther they descend, the fewer competitors remain, and the more completely their specialized physiology determines who can share that space. At the floor of the horizon deep, the amphipods gather where the ocean presses hardest against living tissue. They have made an extreme depth into a boundary, a biological refuge maintained by physics. Their advantage comes from occupying a boundary that excludes much of the competition. Beyond that community, life becomes smaller, more fundamental, and increasingly difficult to recognize by ordinary measures. A xenophyophore begins with something almost impossibly ordinary: one cell. There is no collection of cells forming a body, no separate organs dividing the work. One continuous living structure occupies the sediment, sometimes reaching about zero point 0.1 meters, which is about 4 inches across. For a cell, that is an extraordinary scale. Most cells remain microscopic because their size is constrained by the distance nutrients and chemical signals must travel within them. Xenophytophores have found ways around those limits. These organisms belong to the foraminifera, a diverse group of single-celled protists that build mineral structures around themselves. Their relatives occur throughout the oceans, yet the xenophytophores of the deepest trenches have developed an unusual form. Their bodies extend through delicate internal networks, allowing materials to move across a structure far larger than the cells ordinarily encountered in animal tissues. The outer framework, called a test, is assembled from whatever the seafloor provides. Mineral grains, fragments of shells, sponge spicules, and other particles are gathered from the surrounding sediment and bound together with organic material. The result can resemble a miniature landscape with branching walls, chambers, and passages spreading outward from the living cell. That architecture changes the neighborhood around it. Tiny worms can occupy its spaces. Isopods, bacteria, and other microorganisms attach themselves to its surfaces or shelter within its framework. A xenophytophore, therefore, becomes more than a single organism. Its structure creates a small habitat in which other forms of life can feed, move, and reproduce. The cell itself becomes a piece of infrastructure. Food reaches this world as particles descend from the waters above. Organic fragments settle onto the trench floor, where xenophytophores can capture and incorporate some of that material. Their activity helps redistribute nutrients through the upper layers of sediment, connecting falling organic matter with the organisms living at the seafloor. The process is gradual, yet it contributes to the circulation of matter through an ecosystem far removed from sunlight. Extreme depth may also give these giant cells an advantage. Predators and competitors that dominate shallower environments become less common as pressure rises. Xenophytophores can spread across hadal sediments, forming patches where their elaborate tests become part of the physical landscape. In places, this can produce dense fields of structures, each one adding another fragment of shelter and surface area. Their presence also blurs the boundary between organism and environment. Particles around them become shelter, feeding surface, and physical support. Each structure records something of the sediment passing through its surroundings, turning loose material into a durable living construction on the trench floor. Their size remains the most striking feature. A cell large enough to be seen without magnification seems to challenge the familiar image of cellular life as something confined to a microscope slide. Yet the xenophytophore is still one cell, carrying out the basic processes of living matter across a body assembled from the seabed. The deepest trench, therefore, contains an ecosystem built at several scales at once. Amphipods move across the sediment. Xenophytophores shape the sediment around themselves. Smaller organisms occupy the spaces they create, and through all of it, nutrients pass from falling particles into living tissue and back into the seafloor. The visible structures are only the outer expression of that exchange. Far below them, another layer of life works without sunlight, drawing energy from chemistry rather than from the surface world. At the bottom of the Tonga Trench, food arrives from two directions. Some of it falls from the ocean above, carried downward as fragments of life from sunlit waters. Other nourishment begins in the rocks themselves, where geological reactions provide energy for organisms that have never depended on sunlight. Across most of the ocean, the story begins at the surface. Sunlight enters the upper water. Microscopic algae convert that light into organic matter, and countless animals feed upon the resulting growth. When organisms die, their remains descend as marine snow, a steady rain of particles that can include dead plankton, fecal pellets, and fragments of tissue. The journey can take weeks or months, with much of the material consumed before it reaches the deepest seafloor. Some of that falling material does arrive at the Tonga Trench. It becomes food for scavengers and microbes, linking the deepest sediments to ecosystems thousands of meters above. Yet another source of energy is woven into the same environment, one that begins with the movement of the planet rather than the warmth of its star. Far below the surface, geological processes expose compounds that contain stored chemical energy. Certain bacteria can capture that energy through chemosynthesis, using chemical reactions to build organic matter without sunlight. Hydrogen sulfide, methane, ammonia, and other reduced compounds can serve as fuel when suitable reactions allow microorganisms to extract energy from them. The setting around Tonga is especially suited to this kind of chemistry. The Pacific Plate descends into the mantle, carrying seawater altered within oceanic crust and sediments toward regions of intense heat and pressure. Fluids can circulate through fractures and mineral layers, changing their chemical composition along the way. Volcanic activity above the subduction zone adds another pathway through which chemically rich fluids and gases enter the ocean environment. Those reactions create opportunities for bacteria to occupy the first level of a second food web. Other microorganisms and small animals can graze upon bacterial growth, while larger scavengers consume those organisms. Energy passes from chemistry into living tissue, then onward through a community assembled around reactions occurring in rock and water. This process gives the trench an unusual connection between geology and biology. A movement of tectonic plates becomes a chemical transformation. The transformation becomes microbial energy. Microbial growth becomes food for animals. A process that begins deep inside the planet can therefore end as nourishment for life on the seafloor. The two food streams also overlap. Marine snow supplies carbon and other nutrients from the surface, while chemical reactions provide additional energy from below. Their contributions vary across the trench, depending on sediment, fluid movement, volcanic influence, and the availability of reactive compounds. The result is an ecosystem whose resources arrive through different physical pathways, connecting the atmosphere and sunlight above with minerals and pressure below. Nothing here requires the trench to be separated from the rest of Earth. Every particle sinking through the water carries a history from the surface, while every chemical reaction beneath the seafloor reflects the planet's interior motion. At this depth, those distant processes meet within living cells, turning planetary movement into biological activity. The deepest animals are therefore connected to two worlds at once, one raining material downward, the other releasing energy upward. Together, these pathways make the trench floor part of a much larger planetary cycle. The shape of the Tonga Trench gathers material from the ocean above. Its steep walls descend toward a narrow central floor, creating a natural pathway for particles that might otherwise settle across broad stretches of seafloor. In the horizon deep, that geometry gives falling organic matter a greater chance of becoming concentrated where the trench reaches its greatest depth. Across the surrounding abyssal plain, particles descending through the water are spread over enormous areas. Inside a trench, gravity adds another movement. Sediment can creep down sloping walls, carrying fragments of plankton, fecal material, and other organic remains toward the central axis. Each particle becomes part of a slow accumulation, building a deposit where the supply of material can exceed what would be expected from the surface area alone. That concentration changes the chemistry of the sediment. Microorganisms living within the upper layers consume organic matter and use oxygen as they break it down. Measurements of oxygen consumption in Tonga Trench sediments have shown stronger biological activity than in nearby abyssal plain sediments, suggesting that the trench floor processes incoming organic material at an unusually high rate. The seafloor becomes a place where falling matter is transformed, buried, and incorporated into the sediment. The depth adds another layer to this process. At the horizon deep, the water column reaches about 10,800 meters, which is about 35,400 feet. Material deposited there is separated from the surface by an enormous column of water, while the sediment itself is protected from ordinary waves and most surface currents. Once organic carbon becomes buried deeply enough, its return to the atmosphere can take far longer than the span of a human life. This does not mean every particle remains permanently locked away. Sediments are continually disturbed by animals, chemical reactions, and the gradual movement of material along the trench floor. Some carbon is consumed by organisms, some is transformed into dissolved compounds, and some can eventually move elsewhere. The important feature is the balance. A portion of the organic material arriving at the trench can become buried faster than it is returned to the wider ocean. The surrounding volcanic landscape may strengthen this effect. Erosion from islands and submarine slopes supplies sediment, while the trench geometry directs some of that material toward deeper regions. Organic particles become mixed with mineral grains, creating layers that can preserve carbon within the seafloor. The process links biology, gravity, sediment, transport, and tectonic structure in one continuous system. Across the world's hadal trenches, these environments may account for an important share of the ocean's burial of organic carbon, although the exact global contribution remains difficult to measure. The Tonga Trench is especially interesting because its depth, active sediment supply, steep walls, and productive biological communities work together within a confined space. A place shaped by planetary collision, therefore, performs another task at the same time. It receives material created by life near the surface and carries part of that material into geological storage. The carbon does not disappear. It enters another chapter of Earth's circulation, held within sediment, where pressure, chemistry, and time can keep it separated from the surface world for generations. In this way, the trench floor becomes more than a destination for debris. It becomes a boundary between the fast circulation of surface life and the much slower storage of geological time. The Earth keeps its deepest structures beyond the reach of every drill. The Kola super deep borehole in Russia reached about 12.3 kilometers, which is about 7.6 miles, before engineering difficulties ended it. Beneath oceanic crust, the mantle begins roughly 7 kilometers, which is about 4.3 miles below the seabed. Yet no borehole has ever approached that boundary through oceanic crust. Much of what we know about the mantle, therefore, comes from something that travels through it. Every earthquake sends vibrations through the planet. Seismometers on the surface record the arrival of these waves, measuring their travel times, frequencies, and changing forms. Some waves accelerate through dense materials, others slow, bend, reflect, or disappear when they encounter different physical states. From those changes, researchers can reconstruct structures that remain far beyond direct observation. It is a kind of planetary imaging created by earthquakes instead of machines. The Tonga subduction zone is valuable because its descending Pacific plate generates earthquakes at extraordinary depths. Some originate hundreds of kilometers below the surface, providing natural signals from regions that no instrument could ever be placed inside. When several earthquakes occur along a similar path, their waves can be compared, producing a detailed picture of how the descending slab interacts with the mantle around it. One important boundary lies around 660 kilometers, which is about 410 miles, beneath the surface. Another occurs near 410 kilometers, which is about 255 miles. These depths mark major changes in the minerals that make up the mantle. Pressure alters the structure of those minerals, and earthquake patterns can reveal where those transformations occur. Tonga provides a rich collection of deep events for studying how such changes relate to the generation of earthquakes. The descending slab also carries a thermal history with it. A plate that has spent millions of years cooling near the ocean surface enters the mantle colder than the surrounding rock. Earthquakes within and around the slab allow scientists to examine how that temperature difference influences its strength, deformation, and interaction with deeper layers. Their distribution can reveal internal features that would otherwise remain theoretical. Another clue comes from the double seismic zone, where earthquakes occur along two roughly parallel bands within parts of the descending plate. The spacing and depth of these bands can provide information about water, mineral transformations, and the changing mechanical behavior of the slab as it sinks. Tonga has helped refine ideas about how these processes work, with findings that can inform models of subduction zones around the planet. The value of this natural laboratory extends beyond geology. Because the earthquakes occur at different depths and under changing conditions, researchers can compare them as a sequence rather than treating each event as an isolated signal. That continuity turns Tonga into a long-running experiment written into the moving crust. Subduction zones surround many populated coastlines, and understanding how descending plates deform helps scientists interpret earthquake hazards in regions where people live. Tonga offers a rare opportunity to watch deep planetary mechanics unfold through thousands of natural signals, each one carrying information upward from rock that humans may never reach. The deepest parts of Earth remain physically inaccessible, yet they are not entirely beyond observation. Every deep earthquake sends another message through the planet, and each message adds another line to the portrait of the world beneath our feet. Some movement beneath Tonga leaves almost no trace on earthquake instruments. Between two major events in the years 2009 and 2013, stations on the islands recorded gradual drift toward the trench. The ground was changing position, yet there was no familiar burst of seismic energy marking a conventional earthquake. The movement unfolded across years, measured in millimeters rather than moments. A normal earthquake compresses geological change into a brief interval. Stress accumulates along a fault until rocks rupture and slip, sending seismic waves outward. The ground can shift within seconds, and seismometers capture that energy. A slow slip event follows another rhythm. Fault movement occurs over days, weeks, or months, releasing strain without the sharp rupture that produces ordinary shaking. Global navigation satellite systems can detect the resulting displacement even when people feel nothing. The Tonga observations became especially interesting because the deformation was bounded by major earthquakes. A magnitude 7.6 earthquake occurred in March of 2009, while a magnitude 7.4 deep earthquake occurred in 2013. Between them, researchers identified trenchward displacement together with an unusual reduction in background deep earthquake activity. The pattern suggested a prolonged episode of deformation within the subduction system. There was another piece to the puzzle. The 2009 deformation may have been triggered by a separate magnitude 8.1 earthquake, farther north, whose stress changes traveled through the tectonic system. Researchers proposed two possibilities for what followed. One involved slow slip along the plate boundary. The other involved a temporary acceleration of the descending Pacific plate as the system adjusted its forces. Available observations could not distinguish between them with confidence. That uncertainty is part of what makes Tonga valuable. The region has an extraordinary concentration of deep earthquakes, yet the network of instruments is sparse compared with the complexity of processes occurring underground. A displacement recorded at a station on an island can reveal that something changed far below, while offering limited information about the mechanism responsible. The signal is real, but its meaning requires reconstruction from several kinds of evidence. Elsewhere, slow slip has become an important part of earthquake research. Along the Cascadia subduction zone, repeated episodes of gradual fault movement have been observed because they alter stresses around the locked portion of the plate boundary. Scientists continue examining whether similar processes can influence larger earthquakes. Tonga may contain related behavior, although its deep seismic environment is different enough that conclusions cannot be transferred directly. What makes these events especially intriguing is their scale of perception. A person standing on an island might experience an ordinary day, while the crust beneath that island shifts by a tiny amount. There is no sudden rupture, no visible scar, and no dramatic signal reaching human senses. A coordinate changes in a scientific record, and that small numerical difference becomes evidence of a planetary process unfolding over years. Tonga, therefore, offers a reminder that geological change has more than one tempo. Some movements arrive as earthquakes. Others pass through the crust as gradual deformation, leaving evidence in measurements too small to notice without instruments. In a place where the planet produces extraordinary seismic activity, some of its most revealing motions may arrive without the signature that first taught humans how to recognize an earthquake. For 6 decades, the number at the top of the depth chart shaped the map of deep ocean science. The Mariana Trench became the place where expeditions returned, instruments were refined, and new generations of researchers learned how to work at the greatest pressure on Earth. Its Challenger Deep was visited repeatedly by crewed vehicles, with more than 10 crewed scientific descents before 2019. Across the same span, the horizon deep of the Tonga Trench received none. That difference carried consequences beyond a missing set of photographs. Scientific attention tends to gather around a clear distinction that can be stated in a single breath. The Mariana holds the deepest known point on Earth. Its importance arrives already packaged as a record. The Tonga Trench requires a longer explanation. Its Pacific plate descends rapidly into the mantle. Its surrounding system produces an extraordinary number of deep earthquakes, and its volcanic arc reflects the immense exchange between oceanic crust and the planet's interior. Each of those qualities is scientifically rich, yet none has the immediate simplicity of a depth record. A funding proposal can place a single number on its first page. A research program focused on Tonga has to describe why deep earthquakes matter, why subduction speed changes the behavior of a descending plate, and why the deepest parts of the trench might reveal biological and chemical processes found nowhere else. During those decades, Tonga was not completely absent from science. Seismic stations recorded its earthquakes, and researchers used those records to infer what the descending slab was doing far below the ocean. The distinction was between monitoring and sustained exploration. The earthquake catalog grew, while direct observations of the deepest environment remained scarce. The animals living at the horizon deep were sampled only when dedicated expeditions finally reached them in 2018 and 2019. The same gap appears in the sediment. The trench floor receives organic material from the ocean above, while geological processes shape the chemistry of the surrounding system. Yet the long-term movement of carbon through the deepest sediment has remained difficult to measure at the resolution needed to understand its full importance. Models can describe what might happen. Direct measurements tell us what actually happens. Prestige also shapes what becomes familiar. Repeated visits create maps, time series, instrument records, biological collections, and technical experience that make the next expedition easier to justify. Absence creates the opposite cycle. With fewer observations, fewer patterns become visible, and with fewer patterns, fewer reasons appear to return. Tonga spent much of the modern era caught inside that circular gap, its importance growing faster than the evidence available to describe it. Then, in 2022, the eruption of Hunga Tonga Hunga sent an immense atmospheric and oceanic disturbance across the Pacific. The event revealed how much energy this region can release, while also drawing attention to a volcanic system whose deeper connections had been studied far less completely than its significance might suggest. The pattern is difficult to miss. The second deepest trench was never empty of science. It was full of science that had been easier to overlook because its greatest qualities could not be reduced to one spectacular number. Once researchers finally descended into its deepest reaches, each new observation began filling spaces where assumptions had stood for decades. The surprises were already accumulating. The first specimens returned from Tonga carried more information than their labels could hold. In 2018, researchers lowered baited traps into different levels of the trench, allowing the animals living there to gather naturally around a source of food. When the traps came back aboard the research vessel, they contained thousands of amphipods, representing 10 species. 7 had not previously been recorded from the Tonga Trench, while 3 had not been described from this region of the South Pacific at all. The collection also revealed a community arranged vertically through the water column. Larger adults occupied the greatest depths, while younger individuals were more common higher up. Such separation had been recognized elsewhere, yet the pattern in Tonga was especially pronounced. The distribution suggested that depth itself could divide a population into different ecological spaces, allowing animals at different stages of life to use different parts of the trench without competing for every available resource. Sediment offered another unexpected detail. The floor of the horizon deep contained organic carbon in quantities that did not fit comfortably with predictions based only on productivity at the ocean surface above. Material falling through the water was reaching the trench, becoming concentrated there, and remaining within the sediment. The implication was subtle but important. The trench was behaving less like a passive depression and more like a place where material from the ocean could be gathered, processed, and retained. Then came the direct observations from the deepest point. Before the 2019 descent, researchers had prepared procedures for dealing with sediment that might contain human contamination. Such precautions were familiar from other hadal environments, where fragments of synthetic material and other traces of civilization had already been documented. At Horizon Deep, those expectations found little to work with. The sediment collected from the floor showed a degree of pristine condition that surprised the team. Each result added another small adjustment to the picture. The biological samples suggested an ecological structure shaped by extreme depth. The sediment pointed toward unusually strong retention of organic material. The absence of human debris revealed a seafloor that had remained remarkably isolated from the surface world. None of these findings existed as an isolated curiosity. Together, they showed that the Tonga Trench could not be treated as a generic version of another deep trench. That distinction matters because many scientific models begin with observations from places that are easier to study. Once a pattern appears repeatedly, it becomes a useful expectation for regions that have not been visited. Tonga keeps interrupting that habit. Its rapid subduction, intense deep seismicity, volcanic surroundings, unusual biological zonation, and concentrated sediment processes create a combination that other trenches cannot fully reproduce. For researchers, each expedition therefore becomes more than another visit to a known depth. It becomes another opportunity to compare expectation with evidence. A trap comes back carrying unfamiliar animals. A sediment sample contains a chemical pattern that does not fit neatly into an established model. A floor expected to bear traces of civilization instead preserves the character of a place, almost untouched by direct human contact. The pattern is becoming difficult to dismiss. Tonga does not merely fill a blank space on a map, it keeps changing the questions that the map was meant to answer. And the geological system beneath it continues its work, whether another expedition arrives or not. Far to the south, the Tonga Trench becomes part of something larger. Its deepest channel continues into the Kermadec Trench, forming a connected boundary that stretches toward New Zealand. Together, these trenches trace a subduction system roughly 2,000 miles long, where the Pacific Plate is carried downward along the edge of the ocean basin. The change from Tonga to Kermadec is gradual in the machinery beneath the seafloor. The same broad motion continues along the boundary, although the speed of convergence declines toward the south. At the Kermadec Trench, the deepest point reaches about 10,000 meters, which is about 32,800 feet. That makes it one of the deepest trenches on Earth, yet its scale is often overshadowed by the famous record farther north. There is another moving piece in this system, one that arrives from the open Pacific as the plate travels toward the trench. The Louisville Ridge is a chain of extinct submarine volcanoes carried on the Pacific Plate. Individual seamounts rise from the ocean floor like buried mountains, then approach the boundary and begin their descent. Their arrival can disturb the otherwise continuous shape of the subduction zone. A seamount entering the trench can act like a temporary obstruction. Its hard volcanic mass changes the contact between the descending plate and the overriding plate, shifting where stress accumulates and how the slab bends. Earthquakes may respond to those changes, while the descending plate itself adjusts its path around the irregularity. Far below the surface, the seamount is eventually dragged into the earth and transformed by pressure, heat, and deformation. The process takes something built by volcanoes and feeds it into the deeper machinery of the planet. Along the full arc, these encounters are part of a much larger rhythm. The Pacific Plate approaches the boundary, bends downward, and disappears into the mantle. The surface expression remains a trench, but underneath, the plate is being folded into a descending slab that can carry seawater, sediments, minerals, and volcanic material deep into Earth. The northern Tonga section occupies an especially active position within this system. Here, the Pacific Plate moves at exceptionally high speed. The descending slab plunges steeply, and earthquakes reach extraordinary depths. The volcanic arc above the subduction zone is also highly productive, reflecting the enormous transfer of material and energy occurring along the boundary. Seen from far above, the Tonga Kermadec system resembles a long seam drawn across the ocean floor. Seen through geology, it is a moving interface between surface and interior, extending for roughly 2,000 miles and operating across different speeds, depths, and structures. Tonga forms its most energetic northern expression, where rapid plate motion and deep earthquakes reveal how efficiently the planet can recycle its surface into its interior. The system has been operating for millions of years, and its motion continues on timescales that make human observation feel brief. Every section of the boundary carries its own variations, yet the larger machine remains connected from one trench to the next. The contrast between the two ends also helps explain why one continuous boundary can produce such different earthquakes. Changes in slab age, temperature, curvature, and seafloor structure alter how the descending plate responds as it travels downward. Tonga, therefore, becomes a natural reference point for understanding how subduction behaves when plate motion reaches an unusually rapid pace. The plate arriving at the Tonga Trench carries a history measured in tens of millions of years. Sections of the Pacific Plate entering the boundary are estimated to be roughly 80 to 100 million years old. That age matters because oceanic crust loses heat as it travels across the seafloor, carrying away warmth accumulated when the crust first formed. Older crust becomes colder, and colder rock becomes denser. When that dense plate begins its descent, gravity gives it a powerful downward pull. The process can reinforce itself. A dense slab sinks readily, and its continued descent helps preserve the cold interior of the plate. That keeps much of the descending material dense as it moves deeper into Earth. The weight of the sinking slab then pulls on the plate behind it, a force geologists call slab pull. At Tonga, this mechanism helps explain why convergence remains exceptionally rapid compared with most other subduction zones. There is a subtle distinction between acceleration measured within a human lifetime and change unfolding across geological ages. No person watching the horizon would see the trench retreat from one year to the next. The Pacific Plate would appear fixed beneath the moving ocean. Across millions of years, however, the same forces can shift the position of the trench, reshape the volcanic arc, and redraw the floor of the Southwest Pacific. South of the trench, the Lau Basin records part of this adjustment. As the subduction boundary migrates, the crust behind the volcanic arc is stretched and pulled apart. New seafloor forms along spreading centers, gradually widening the basin. The geometry of the arc changes with it, because the position of volcanic systems depends partly on the shape and depth of the descending slab below. Those changes are connected through the same continuous movement. A slab descending into the mantle influences the shape of the trench. Trench retreat alters the space available behind the arc. Spreading creates new crust within that space, while volcanic activity responds to the changing relationship between the surface and the material descending below. Each process feeds into the next, producing a landscape that is always being revised, even when the revision is too slow for human eyes to follow. The Pacific Plate itself is therefore more than a rigid floor beneath the ocean. It is a cooling, aging body moving across Earth while gradually acquiring the density that allows gravity to draw it downward. Once subduction begins, the descending slab becomes part of the engine driving the motion around it. Across a few centuries, these movements disappear into the background of ordinary human experience. Across a few million years, they can relocate trenches, open basins, rearrange volcanic chains, and transform coastlines. The Tonga system is an example of geology operating through accumulation rather than spectacle, with countless small movements adding together until an entire region has taken a different shape. Above this machinery are islands, ships, observatories, and communities. Human lives occupy a thin interval within a process that began long before any of them existed. The same boundary that produces deep earthquakes and volcanic change also passes close to places where people build homes, travel across the sea, and watch the weather. The geology may unfold on its own immense clock, while its consequences remain part of human time. Island by island, the kingdom of Tonga rises from a process that begins far below the reach of daylight. The archipelago contains about 170 islands scattered across roughly 700,000 square kilometers, which is about 270,000 square miles of the South Pacific. Around 100,000 people live among these islands, within a landscape whose foundations are tied directly to the descent of the Pacific Plate. Human settlement began roughly 3,000 years ago, placing Tonga among the earliest settled island groups of Polynesia. Generations of navigators later crossed enormous stretches of ocean in voyaging canoes, carrying people, plants, animals, and traditions between distant islands. Their routes formed a maritime world whose reach extended across thousands of miles, guided by knowledge of currents, winds, stars, and the changing face of the sea. The land itself belongs to the volcanic arc created above the subduction zone. As the Pacific Plate descends, water and other materials carried downward help alter the rocks above the slab. Melt forms within the mantle, rises through the crust, and feeds volcanoes that gradually build islands above the ocean. The process is spread across immense distances and deep layers of earth, yet its final expression can be as familiar as a shoreline, a hillside, or soil cultivated for generations. At the center of this relationship lies a depth of about 10,668 meters, which is about 35,000 feet beneath the sea surface. That distance separates ordinary human life from the deepest machinery of the trench. The ocean above may appear unchanged from one day to another, while far below, plates bend, fracture, and descend into the planet. Tonga's islands also carry memories of this movement. Earthquakes and tsunamis have appeared repeatedly within the historical and oral record, becoming part of how communities understand their surroundings. Stories, warnings, places of refuge, and inherited knowledge can preserve traces of events that occurred long before modern instruments began recording the ground. Geological processes become woven into culture through generations of observation. The relationship reaches in both directions. The subduction system creates the volcanic foundation on which communities live, while the people who inhabit those islands continually interpret the signs produced by that same system. A tremor beneath the sea, a change in the shape of a shoreline, or the distant sound of an eruption can connect an ordinary day with forces operating far below it. For centuries, this coexistence formed part of the natural rhythm of island life. Modern science has added instruments, measurements, and models, yet the fundamental arrangement remains unchanged. The land is the surface expression of a much deeper process, and the ocean surrounding it is part of the same geological system. In this setting, the boundary between geology and human history becomes unusually thin. A volcanic island can be a home, a garden, a harbor, and a monument to processes occurring thousands of meters below. Every generation inherits both the land and the forces that shaped it, living on a surface that is still being made. The scale of that connection is easy to overlook when viewed from shore. Coconut palms, villages, reefs, and cultivated fields occupy only a thin layer at the top of the system. Below them lies a descending plate, a rising volcanic chain, and a mantle that continues to reshape the boundaries of the islands. Human time rests on geological motion. January 15th, 2022 began as another day in the island kingdom of Tonga. Then Hunga Tonga, Hunga Ha'apai erupted with extraordinary force, sending ash, gases, and seawater into a world inhabited by communities that had spent generations adapting to the presence of volcanoes. This time, the scale reached far beyond the familiar rhythm of island hazards. The eruption produced several kinds of waves at once. Water was displaced near the volcano, while powerful atmospheric pressure waves traveled outward and helped generate additional tsunamis. On Tofua Island, the tsunami reached about 45 meters, which is about 148 feet above sea level. On Tonga Tapu, the country's main island, waves reached about 17 meters, which is about 56 feet in some locations. The numbers describe height, but they also describe how quickly the boundary between ocean and land can disappear. Ash spread across settlements and farmland, coating roofs, roads, gardens, and water collection systems. Around 85% of Tonga's population was affected by the disaster. Villages were damaged or destroyed, agricultural land was covered, and freshwater supplies became difficult to use. The eruption therefore reached into ordinary routines, touching food, drinking water, transport, homes, and the basic work of rebuilding a day. Then another kind of separation followed. The submarine fiber optic cable connecting Tonga with the outside world was severed. The cable stretched about 827 kilometers, which is about 514 miles, across the seafloor. With that connection broken, reliable international communication was disrupted for more than 5 weeks. Messages became harder to send, information moved through slower channels, and a nation already dealing with ash and damaged infrastructure found itself further separated from the wider world. The human toll remained smaller than the physical scale of the eruption might suggest. 4 people in Tonga died from the disaster, while 2 people in Peru died after tsunami effects reached the South American coast, more than 10,000 kilometers, which is about 6,200 miles, from the volcano. Around the Pacific, instruments and coastal observations recorded waves and atmospheric disturbances far from the source, showing that the eruption had crossed several boundaries at once, from ocean water to atmosphere, from geological force to communications infrastructure. Recovery required the patient return of ordinary things. Ash had to be cleared from farmland. Water systems needed restoration. Damaged communities needed supplies and transport. The cable required repair before dependable digital contact could fully return. For a small island nation, the event became a lesson written across every layer of daily life, showing how a process that begins deep in the earth can reach kitchens, fields, harbors, schools, and the invisible pathways connecting people across oceans. The atmosphere carried part of the eruption's energy across enormous distances as well. A pressure wave traveled around the Earth multiple times, while sound and infrasound were detected far from Tonga. For people living near the volcano, the event was therefore both local and planetary, arriving through channels that ordinary disaster planning had rarely considered together. For Tonga, geology had become infrastructure, communication, water, agriculture, and human safety at the same moment. The boundary between natural hazard and daily life had almost disappeared. The eruption also changed the scientific record. Modern instruments captured atmospheric waves, unusual tsunami mechanisms, and disturbances that traveled through both air and sea. The event became a rare natural experiment in how a volcanic system above a deep subduction zone can couple the ocean, atmosphere, land, and human infrastructure in a single afternoon. Tonga was living directly beside a geological process whose reach could no longer be measured only in earthquakes and eruptions. The map of the Tonga Trench looks more complete than it really is. A line can mark the trench, a number can describe its depth, and a handful of expeditions can place names beside specimens. Yet those marks represent only a narrow sampling of a system extending across immense distances and through layers of water, sediment, and rock that remain difficult to reach. At horizon deep and across the surrounding hadal zone, the known species represent only a fraction of the living community. Deep sea taxonomy moves at the pace of careful collection and comparison. A single expedition may gather specimens from a few carefully chosen sites, then return with material that requires months or years of laboratory work. Some animals resemble known species, closely enough to complicate identification, while others carry physical traits that suggest a lineage has been evolving apart for a long time. The inventory, therefore, grows slowly, even when the ecosystem itself continues changing. Southward, another uncertainty begins where the Tonga system approaches the Kermadec region. Scientists can identify broad similarities between the two hadal environments, yet the precise boundary between their animal communities remains imperfectly mapped. The Louisville Ridge adds another layer to that geography, as it is carried toward the trench and progressively drawn into the subduction system. Whether Tonga and Kermadec share a broadly connected biological community or contain more distinct populations shaped by their geological separation remains unresolved. The sediment holds another missing record. Organic carbon reaches the trench from the ocean above, becomes incorporated into the seafloor, and can remain there for long periods. Measuring that burial over meaningful stretches of time is difficult because the process varies with storms, productivity, currents, sediment movement, and the changing biology of the surface ocean. Without sustained measurements, the contribution of the Tonga Trench to long-term carbon storage remains poorly constrained. A place that may gradually preserve material from the surface world has never been watched long enough to reveal its full rhythm. The same uncertainty follows the earthquakes. Slow slip has been detected in the region, yet its relationship with larger earthquakes remains unresolved. It may represent one part of the normal movement of an exceptionally active plate boundary. It may alter stresses around locked sections of the fault. It may also have little value for predicting a destructive event. The available record is too short and too uneven to separate these possibilities with confidence. Far below the reach of ordinary observation, another clock is running. Plastic arriving from the wider ocean is beginning to enter even the deepest environments, while currents and sediment pathways may change the places where that material settles. The condition of the trench floor decades from now cannot be predicted with precision. Even the biological consequences of that gradual arrival remain uncertain. Volcanic activity carries its own timetable. Another major eruption within the Tonga Arc is part of the geological future of the system, yet science cannot specify its hour, year, or century. The same subduction continues feeding the arc, while magma gathers and moves through a crust that is never truly finished. The unknowns are therefore not empty spaces waiting for convenient answers. They are active parts of a living geological system, changing while instruments measure them. The map remains incomplete because the trench itself keeps moving, carrying its evidence deeper into the earth and leaving each generation with another layer to discover. Some places on Earth carry our fingerprints everywhere. The moon has footprints. Everest has climbing routes, camps, discarded equipment, and survey markers. The South Pole has research stations. Even the deepest known point of the Mariana Trench has received human visitors. Far above the weather, synthetic compounds created by civilization have entered the atmosphere and can be detected across the planet. Horizon Deep belongs to a different category. Its floor remained largely untouched for reasons that had little to do with deliberate preservation. Reaching it requires specialized vessels, a submersible capable of enduring enormous pressure, favorable conditions at sea, and years of planning. For decades, those requirements kept the trench outside the practical reach of most scientific programs. The absence of human traces became an accidental consequence of distance, depth, cost, and limited attention. That distinction matters. A protected forest can remain intact because people decide to leave it alone. The Tonga Trench endured because almost nobody could reach it. Its condition therefore carries an unusual kind of history. The pristine sediment, the organisms living within it, and the physical landscape below the water are not monuments created by conservation. They are remnants of a place that remained beyond the ordinary boundaries of human activity. The first successful crewed descent to Horizon Deep in 2019 changed that boundary. A human vehicle reached approximately 10,823 meters, which is about 35,509 feet, below the surface of the South Pacific. The journey took the human presence of the surface world into a realm that had previously existed almost entirely through measurements, models, and distant signals. There is something rare about encountering a place during the brief interval between being unknown and becoming thoroughly documented. Before every sediment layer has been sampled, before every organism has been cataloged, and before every physical process has been measured across time, the landscape retains a kind of scientific openness. Its story has already been unfolding for millions of years, yet much of that story has never entered a human record. The Tonga Trench occupies that interval now. Instruments can extend our senses. Cameras can return images. Samples can travel upward into laboratories where their chemistry and biology can be examined in detail. Each new observation turns one blank space into a measured point, one unfamiliar organism into a described species, one uncertain process into a better constrained idea. The mystery becomes smaller in one direction, while the remaining unknowns take clearer shape. That process does not diminish the trench. It reveals how little a civilization can know about a planet it has inhabited for thousands of generations. The deepest parts of Tonga have continued their work through earthquakes, volcanic activity, sediment movement, and the steady descent of oceanic crust, indifferent to whether anyone was watching. Human attention has finally reached the edge of that world, but attention is temporary. Expeditions end, instruments are recovered, research programs change, and ships return to shore. The geological system remains. Far below the routes of ordinary travel, the trench continues to receive the Pacific plate, reshape the seafloor, and alter the islands above it. Its processes require no witness and record no audience. The Tonga Trench does not know we are here. For the trench, observation changes nothing about the forces already moving through it. The Tonga Trench carries a history that begins far outside the reach of human memory. Its formation stretches back roughly 50 million years, when movements of oceanic plates began shaping the boundary that would become this deep Pacific system. At that time, no human lineage existed. The planet was already conducting its long experiments in pressure, heat, volcanism, and renewal, with no observer waiting to record the results, while continents shifted and oceans opened around them. The first members of the human lineage appeared only around 6 or 7 million years ago. Modern humans arrived much later, roughly 300,000 years ago. Written language, which gave one generation a durable way to leave knowledge for another, is only about 5,000 years old. Against those spans, the history preserved by a written record occupies a remarkably narrow interval. For almost 50 million years, the Tonga system continued without a human account. Its earthquakes moved through the crust, volcanoes rose, changed, and disappeared. New ocean floor formed as the Lau Basin opened. Sediment settled into the deepest parts of the trench, where organisms adapted to pressure and darkness. None of these processes required a witness. They followed the physical conditions around them, repeating across immense stretches of geological time. During those same ages, countless branches of the human family appeared and vanished. Species changed, populations spread into new environments. Others disappeared completely, leaving bones, tools, fragments of shelter, and traces in the genetic record. Civilizations eventually emerged, built cities, crossed oceans, created writing, and developed instruments capable of detecting movements too small for the human senses. Through all of it, the Tonga Trench continued its descent into the Pacific. The eruption of 2022 belongs to this much longer sequence. For people living on the islands, it carried consequences that reached homes, water supplies, communications, and daily life. Geologically, however, it was one event within a system whose history extends across tens of millions of years. The trench does not mark its eruptions according to human calendars. It has no sense of anniversaries, records, or milestones. Its future is similarly difficult to place inside a human frame. Oceanic crust will continue moving toward the boundary, while the forces driving subduction remain active. The trench will change shape. The volcanic arc will shift. The Lau Basin will continue spreading, altering the geometry of the Southwest Pacific across millions of years. A future Earth may look unfamiliar, even while the same basic machinery continues beneath the ocean. 10 million years from now, the islands may occupy different positions. 100 million years from now, coastlines, volcanoes, and ocean basins may bear little resemblance to those known today. Yet geological processes will still be shaping the planet through movement, pressure, melting, cooling, and accumulation. Human instruments will eventually disappear, whether through abandonment, replacement, or the transformation of civilization itself. The measurements they made will remain for a time, stored in archives, carried through institutions, and perhaps remembered by descendants we cannot imagine. The Tonga Trench will require none of this. It will continue without records, without witnesses, and without any awareness that it was ever observed. And that leaves geology at the edge of something it cannot measure, the meaning of a world that continues after the observer is gone. Geology gives the people who study the Tonga Trench an unusual companion, time. A process can be watched for a lifetime while remaining almost impossibly old. The trench began taking shape millions of years before modern humans appeared, and the forces moving its plates will continue long after our own history has become a thin layer in the record of Earth. Against that scale, a human life is brief, almost like a pause between larger movements. Still, brevity does not make a life insignificant. Around 100,000 people live among the islands of Tonga, carrying histories through families, language, ceremony, work, and memory. Their lives are measured in seasons, generations, journeys, celebrations, and ordinary mornings. The volcanic islands beneath their homes were shaped by processes that operate over immense spans of time, yet the meaning of those islands belongs to the people who inhabit them. The eruption of 2022 brought that connection into sharp focus. Crops were covered by ash. Freshwater sources were contaminated. Communications were interrupted, when the submarine cable was severed, separating communities from one another and from the wider world. A geological event could be indifferent to individual lives while still entering those lives completely, changing what could be grown, what could be consumed, and how people could reach one another. That tension is part of living on a moving planet. Earth does not provide a fixed stage beneath human civilization. The ground beneath every settlement belongs to a system of shifting plates, rising magma, cooling rock, erosion, sediment, and pressure. We build roads and gardens upon it, draw borders across it, give places names, and inherit stories connected to particular shores. Under all of those human arrangements, the planet continues its own physical work. The Tonga Trench makes this relationship unusually easy to picture. From the sea surface to the floor of Horizon Deep, the descent reaches about 10,823 meters, which is about 35,509 feet. That immense vertical distance is only one part of the system. Earthquakes can begin much deeper within the descending plate, where rock is subjected to pressures and temperatures that transform how it behaves. Human civilization occupies a remarkably narrow layer of this moving world. We measure years, preserve records, repair damaged infrastructure, and plan for the next generation. Geological processes measure themselves through the changing shape of ocean basins, the birth and destruction of crust, and the gradual migration of volcanic arcs. Both scales exist together, overlapping without needing to agree. Human concerns can feel immediate because they are immediate to the people living them. Geological change can feel distant because its largest movements unfold beyond a single lifetime. Neither scale cancels the other. There is no place outside this system where humanity can step aside and watch from a distance. Every harbor, forest, field, and city rests upon material that is part of the same restless planet. The Tonga Trench only makes that relationship visible with unusual clarity. Its presence does not diminish the human story. It places that story inside something larger, something that began before memory and will continue beyond memory. The people of Tonga live on islands created by geological forces, and they have made those islands into a home. The trench has one more thing to say. It says it without words. At the floor of Horizon Deep, the world has been reduced to pressure, temperature, chemistry, and motion. The water rests at roughly 35 to 37 degrees Fahrenheit. Above the sediment, more than 16,000 pounds of pressure presses against every surface. There is no familiar landmark to organize distance. There is only the physical condition of the deep ocean. Across that floor, amphipods move through the sediment, feeding on material that has descended from the waters above. Xenophyophores gather particles over long periods, building their delicate bodies from what settles around them. Bacteria use chemical energy associated with the surrounding geology, sustaining forms of life without sunlight. Each organism occupies a small place within a system shaped by pressure, falling particles, and the chemistry of rock and seawater. Far above them, the Pacific Plate continues its journey toward the trench. At Tonga, the plate moves at roughly 9.4 inches each year. The distance is tiny by human standards, yet the motion continues. A year adds another small displacement. A century adds many more. Across millions of years, those increments become enough to consume oceanic crust and reshape the boundary between Earth's plates. The movement also reaches into the Lau Basin, where the crust behind the volcanic arc is being pulled apart. Molten rock rises into the opening, cools, and becomes new ocean floor. The basin changes as this spreading continues, while the volcanic arc responds to the shifting relationship between the descending plate and the mantle above it. The surface may appear stable from a passing vessel as new crust forms far below. Hunga Tonga belongs to this same machinery. After the eruption and collapse of 2022, the volcanic structure began a new phase of construction. Rock and ash accumulated around the altered crater while magma remained connected to the deeper system. The volcano does not exist apart from the trench. Its history is linked to the plate that descends, the mantle that responds, and the crust that rises above the boundary. Then there is the South Pacific itself, extending across distances that make individual geological features difficult to hold in the mind at once. Its surface carries waves, weather, clouds, and ships. Sunlight reaches the upper ocean, while the deepest floor remains beyond its reach. Between those layers lies a connected world of gravity, circulation, sediment, and heat. Above the ocean are the islands of Tonga. Above them is air, and beyond the atmosphere are stars. People wake, work, travel, raise families, and sleep while the plate continues moving underneath the entire story. The trench has no need for a name to perform its work. Naming it gave humans a way to place a particular point on a map and speak about it together. Reaching the floor in 2019 gave us a direct encounter with a place that had existed for millions of years without human observation. The descent did not make the trench begin. It made our awareness of it begin. That distinction reaches across the whole story. The Tonga Trench is a moving boundary, a living habitat, a volcanic system, and a record of planetary change. Its processes continue, whether measured or forgotten. The rock keeps moving through the South Pacific, carrying the machinery of Earth forward one small increment at a time.